Welcome to Robotics, a brief overview. This one's kind of a doozy, but it's the only lesson in this unit, so buckle down. You should probably have your robotic overview notes document open. Make sure you follow the directions at the top of that. It's named correctly. Share it when you're done, and let's get started. So first, definitions. Robotics is a science and technology of robots, their design, manufacture, and application. And the word was first used in print by Isaac Asimov, and that was in 1941. It was a book he wrote called Runaround, so just a little background on that. Robots, the word robot was coined by Carol Kapik in his 1920 play. It means drudgery or hard work, and that's a pretty good definition based off what they do. So please watch this short video on some robots. You'll get to see some kind of an action. Pretty cool.
Industrial robots
Okay, seriously, whose voice is that deep?
have either a hydraulic, electric, or pneumatic power source and are available in various configurations. These configurations range from the relatively simple, having a body with an arm that extends and retracts, to the very complex, having a body, upper arm, lower arm, and wrist. These varying robot configurations are distinguished from each other by the number of degrees of freedom or axes of motion available to the robot. The number of axes helps establish the dexterity of the robot and its overall capability. Robots may have as many as 7 axes of motion, including 4 arm motions and 3 wrist motions. These axes, or joints, are either linear in motion or rotary. Another important characteristic of an industrial robot is its work envelope. This represents the robot's maximum reach in all directions. It varies with the robot's configuration and overall size. Industrial robots are generally classified on the basis of their arm's geometric configuration, with the primary types including rectangular arm robots, selective compliant articulated robot for assembly or SCARA robots, and articulated or jointed arm robots.
So now on to parts of a robot. You have manipulator, power supply, and controller. And so we're going to take a look at each one of these in detail. So the manipulator has joints, grippers, process tooling like drill bits, effectors. All these are at the end of the manipulator. Now robotic arms typically have 4 to 6 degrees of freedom. If you have all 6 degrees, then you can move, you can translate or slide in the X direction, the Y direction, and the Z direction. But then you also might have roll, pitch, and yaw. So roll is kind of moving along this direction, usually depending on which direction you're talking about, coordinate you're talking about. Yaw, and then pitch up and down. So another way you can think of it is sliding in the X, Y, and Z, and then rotating in the X, Y, and Z direction. So all of those different options gives you 6 degrees of freedom. If we look at the power supply, it can be electric, hydraulic, or pneumatic. Electric is the most common, it's what we have, and motors might be servo or step, but we're going to talk about the difference between these. Servos aren't quite what you think they are based off of Vex Robotics. There's a little more to them than what we've seen. And then the third thing is a controller. It is the brains of the robot, and it generally will store data if it's recording data. Now, why do we use robots? We use them to reduce labor costs, eliminate dangerous jobs. Like if you're doing welding, these 4 are doing some welding. Increase output rate because you can work 24 hours a day, and improved product quality, along with reducing waste. Because robots, they can go from place to place. They never make a mistake, usually, as long as it's a good quality robot. So we're going to look at these different systems, and should be down on number 7, and 5 different types of robots here. So first, looking at what that's going to be, an industrial robot is a complex technical system consisting of several subsystems operating together. So the subsystems we're going to look at are kinematics, control systems, and drive. And these will help you understand then those 5 different robots. So kinematics refers to the spatial arrangement according to the sequence and structure of the axes of movement in relation to one another. So how do the axes X, Y, and Z move with relation to each other? Depending on how they move, Then the industrial robot might have Cartesian coordinates, cylindrical coordinates, polar coordinates, or jointed arm. And we're going to look at those four along with a fifth one, and that is the 5 different options you have on number 7. So starting out as a Cartesian coordinate robot, it moves in the XYZ direction, generally an arm, and they are all lateral, longitudinal, and vertical motion. They all slide. So here's an example of one of them, and it shows a work envelope. So we're sliding in the Y, X, and the Z. It has a rectangular work envelope, and the work envelope, again, is just the area that the robot can work. It also looks like the Z claw here can go in this sort of direction. So that gives you another degree of freedom, and it looks like 4 degrees. That would be a yaw. Here's another example of a Cartesian coordinate. This one is like our milling machine. And so this could be done, an arc welding robot, maybe handling at machine tools like a milling machine. It could be used for assembly operations, application of sealants, because you could see something moving and sealing around something here, or picking and placing up things. So again, that's our milling machine. A cylindrical coordinate is similar to Cartesian, but it has a column and a base. The column is able to rotate, so you can see we can rotate here. The Z moves up and down, and then the Y moves back and forth. And it also looks like this can sort of pivot back and forth, so it looks like it has pitch. So that would be a 4th degree of freedom there. So again, you have a radial rotation around the Z-axis, or the base. You have a Y-axis for longitudinal and the Z-axis for vertical. A cylindrical coordinate robot has a cylindrical work envelope, so you can see it kind of makes the cylinder. It can't turn around behind itself, usually because of a controller that's back here. So this is an example of a cylindrical control robot, and that's its work envelope. Here's another example of one and some different things it can do: assembly, tool, spot welding. A lot of robots can do a lot of similar operations. So the third one is polar coordinates, and this is a rotary base, a elevation pivot, and then a telescoping extension. So it has 2 rotations and then a translation or a longitudinal motion. And a polar coordinate will allow it to move in sort of a spherical work envelope. You can see it's a hollowed out sphere, because this can't slide all the way in. It can't grab something right in the middle of this thing, but it does have sort of a spherical like shell. And again, it can't reach around the backside usually because there's a control arm there. And here's another example of polar coordinate, good at machine tools, spot welding, handling again, and anything where you'd want to move up, usually moving up rapidly is good for that. And jointed arm robot. So this resembles a human arm. It usually stands on a rotating base. It has articulated shoulder and elbow joints. So here you have a base which is rotating in this direction, and it's rotating around the Z direction. Then you have a shoulder, elbow, and wrist. And this is the type of robot that we have in the milling room. So this has a spherical work envelope, and it can reach in a lot of different places. And this arm, you can see, since this J4 can move in, it can actually reach a lot greater distance inside itself, because if this whole arm comes back, then you can reach really, really close to the base in there. So again, here's a jointed arm robot. It's really good for assembly, again, handling, welding, spray painting, because it can move kind of in all directions. It has so here's an example of an axis range, just kind of a schematic of that, and you can see that it can't generally go all the way in a circle because of maybe wire limitations that getting caught and a controller base in the back.